Hello everyone and welcome to another in-depth minute concept which is about physics, particularly kinematics and UAM. So in the last video we discussed how to figure out which kinematic equation to use based on what missing variable there is, and we also were able to define kinematics as well as UAM. However, now in this video we're going to be trying and applying these equations in actual situations. So in order for us to figure out how to understand UAM and how to use them in our calculations, we need to first understand the purpose of each equation here. So as I mentioned in the last video, this would be a recap for those who were able to watch. Each equation is missing one specific variable. So for example, in equation 1 rather, there is a missing variable of delta x, so there is no change in position. For number 2, there is actually no acceleration. For equation number 3, there is no final velocity. And for equation number 4, there is no time. And now why is this important to know? It's because in most questions, they will be giving every single variable needed except for one. Now, these variables of course are going to be derived, those missing variables. However, if they really do not give, for example, time, it's impossible for you to use any of the other equations because that will just get you an equation with two variables, which is a lot more difficult. Possible, I'm pretty sure, but a lot more difficult. So that's how we pick the best equation. So let's give it a try using this sample problem. An airplane accelerates down a runway at 320 meters per second squared for 32.8 seconds until it finally lifts off the ground. Determine the distance traveled before takeoff. Okay, so now we have to isolate first our given values. In order to figure out the given values, we need to list them down one by one. So it accelerates down a runway at 3.20 meters per second squared. So that means our acceleration, or A, is 3.20 meters per second squared. We also have time, which is 32.8 seconds. And let's see if we can figure out anything else here. Determine the distance traveled before takeoff. We know that we have to determine, and we have to find. RTF stands for required to find. We are required to find delta x. So among these, we're actually missing one more variable. And how do we know that? It's because if you notice in every equation there's four variables given, and you're only supposed to be missing one. So what are we missing? We're actually missing initial velocity. And how do we determine that? We apply logic into the question. So as you can see, an airplane accelerates down a runway at 3.20 meters per second squared. Now an airplane cannot start running without first being at rest in a runway, because an airplane is heavy, and obviously that's why there's a runway in the first place. It needs a place to start from rest. So our initial velocity is actually 0. That is simply from the question itself. Now, how do we determine the distance traveled before takeoff? So if you notice, in this equation here, we are missing a certain variable. Let's see which one we can figure out. We're not given a variable for final velocity. So that means we have to use the third equation, which is delta x is equal to VO, or initial velocity, times time, plus 1/2 acceleration times time squared. So now let's use, I'll use the green pen here. So our delta x, which is what we're looking for, or rather I'll use the yellow, so it's the same. Our delta x is equal to V0, which is 0. Okay, now I'll use the green pen. 0. Wait, that looks too much like yellow. Sorry. Okay. 0 times time, which is essentially just 0, so we'll just leave it at that, plus 1/2 acceleration, which is 3.20, times time squared, which is 32.8 squared. So we can simplify the equation from here. We can get delta x is equal to 3.20 divided by 2 is just 1.6 times 32.8 squared. So now plugging that into your calculator, 32.8 squared is 1075.84, and then we multiply that by 1.6, which should get us 1721.344. So delta x is equal to 1721.344. Rounding off to the correct amount of significant figures, since it's multiplication, we have to count the least amount of significant figures here. We're going to get 1720. Underline the third to show that that's the last significant number. Okay. So that is how you get the answer for this question. Okay, so next, let's try this one. Allow me to duplicate this for everyone's guidance. Oops. Okay. Excuse me. Okay, so for this question, we have to do the same thing, and we're going to first identify the variables that are given. So based on this question, we are given initial velocity. A race car accelerates uniformly from 18.5 meters per second to 46.1 meters per second in 2.47 seconds. So when we see the word from, that means we start from somewhere. And if we start from somewhere, that means that we are given an initial starting point. And therefore, when we write down our given, our initial velocity is 18.5 meters per second. And our final velocity is after 2. That's our ending point. 2 is the signifier or the signal word for the ending. So 46.1 meters per second. And we're also given the time, which is 2.47 seconds. Alright, so now we have to determine the acceleration of the car as well as the distance traveled. So we have two RTF here. Our RTFs are acceleration and the distance traveled, which is delta x. So how do we simplify this problem? Well, since we have two RTFs, we need to use two different equations, and that also means you have to split the problem in two. So clearly, if we're able to solve for acceleration, we can also solve for delta x, or even without solving for the acceleration, which would just essentially make our life a bit easier, we can just go ahead and go straight for doing them both at the same time. However, let's just do them one at a time first. So acceleration is derivable from most of the equations except for the second one, since the second one has no acceleration involved. Now, based on the given variables, we have initial velocity, final, and time. Which one can we use to derive acceleration? Now, we also don't have delta x, so we can't use 3 and 4. We also can't use 2, so that leaves us with 1. So our working equation for acceleration would be acceleration is equal to, if we reorganize this equation here, actually allow me to show you guys how to reorganize that equation. So we're given equation number 1, which is v0 plus at, and we want to get a alone. So what do? First, we're supposed to isolate this set of variables here, that term. So we're going to transpose this to the other side, and we transpose by subtracting initial velocity from both sides. So vf minus vo is equal to at, and now we want to get a alone again, so we have to divide at by t on both sides. So we get vf minus vo over time, and that's our acceleration. So that is how you derive a formula. Now, based on this formula here for acceleration, we just have to plug in our values. So let's put this here on the side. Given that we have this new working equation, I'm going to remove everything else on the top, just so that it's not confusing anymore. Okay. Allow me to just rewrite that over here. So replugging in our values, we're going to be able to get Vf, which is 46.1, minus 18.5 over 2.47. Plugging this into your calculator, you would get 46.1 minus 18.5 divided by 2.47. That should be 11.17. 11.17, this is acceleration, so this is meters per second squared. Okay, and since we have 3 significant figures, we just have to round off. This is 11.2 meters per second squared. So therefore, our value for acceleration is 11.2 meters per second squared. And we got that using equation number 1. Now let's just put this up here. Now for delta x, we can solve it again using any of the equations, given that we have all of the variables needed. Now actually we can see that we have every variable needed for kinematics, so let's just choose the simplest one. Obviously though, we cannot use equation 1 since it cannot solve for delta x. However, we can use equation 2, since equation 2 is quite straightforward. Delta x should be equal to Vf plus Vo over 2 times time. Now if we plug in our values here, we should be able to get 46.1 plus 18.5 divided by 2 times 2.47. So now plugging this into the calculator once more, 46.1 plus 18.5 divided by 2, that's equal to 32.3, and multiply that by 2.47, you should get an answer of 79.781. And since we have once again 3 significant figures, this rounds off to 79.8 meters. And now that is our final answer for this question. The total distance traveled by the race car would be approximately 79.8 meters. So here it is. And we got them by using equation 1 and equation 2. So now let's move on to another question, and this time it's about free fall. Free fall is a question that a type of question that also involves that also involves kinematics, particularly because, as you can see here, we have constant acceleration when we're using a car, and free fall is actually the motion of an object as it's dropped, and gravity is actually a value of acceleration. So our known value for gravity, which is 9.8 meters per second squared, this g over here actually stands for acceleration due to gravity. So in other words, any object that is falling has the same acceleration. And while air resistance is a thing, in most situations, in most tests, acceleration due to gravity disregards air resistance, as air resistance actually just balances out the force of gravity. At the end of when an object is no longer being affected by air resistance, it actually just has the same acceleration as gravity. So that's why a question involving free fall is actually UAM as well. So now let's go about again getting our given to solve this question. Okay, so free fall once again has uniform gravity, so a uniform acceleration in the form of gravity. So let's just leave that already. Now, if Upton free falls for 2.6 seconds, that means we have time. 2.60 seconds. What will be his final velocity and how far will he fall? Okay. Oh, wait. Allow me to get the other equations. So we're missing final velocity and we're missing delta x. So let me copy paste the equations once more. Okay, so here you go. Here are our given again. Okay, now an important part of free fall is that we have to pay attention to the nature of the object being dropped. Now, it's not actually always being dropped. I can throw an object going down and it would still be in free fall. So it's important to know if the object has an initial velocity or not. So now we have to go back to the question. Reading the whole thing, we see that Upton Chuck is riding the giant drop. Drop is your keyword here. To drop something means you're holding it in place and then you're going to let go, meaning it starts off at rest, meaning our initial velocity is actually 0. So from 0 meters per second, we can get any value that we need from here, since we have 3 variables already. So we can derive one more and then we can get all of the values needed. So we can start with perhaps final velocity. Since we have initial velocity, we have time. Wait, allow me to move this one so that it's more seen. Okay, we have time and we have acceleration. And g is acceleration again. Okay, so using those given, let's try using equation number 1. Okay, so equation number 1 gets us initial final velocity. So let's write it down again here. V0 plus AT. So that means that VF should be equal to 0 plus 2.6, or let's do it in the correct order, 9.8 times 2.6, 2.60 rather. So putting that into the calculator, you would get 25.48 meters per second. So that is our final velocity. And we got that again using first kinematic equation. Oh, don't forget to round off. So let's round off here at the required to find portion. Rounding off again uses significant figures, so check which measurement is the least accurate or has the least significant figures. Since we have 3, that means we have to round off to the third decimal place. So let's remove, or the third significant figure rather. So 25.48 becomes 25.5 meters per second. Okay, now from here we have to get delta x. Now reviewing our values, now we have all 4 variables that can lead us to the 5th. So we can use any equation here again. What would be the easiest equation to use? Now given that we don't have any initial velocity, or there is, however it's 0, so it's negligible, we can actually use equation 3 this time. But equation 2 also works. Equation 3, it's a bit more straightforward and it has little steps. Since if you notice, v0 times time, that's 0 times another number. So immediately we cross out this variable right there. So let's try using equation number 3. Let's make this smaller. Okay, there. Let's use equation number 3. Equation number 3 again is delta x is equal to v0 times time. So delta x, since we know that this should be equal to 0, let's just make this 0 already, plus 1/2 times 9.8 times 2.60 squared. So we can simplify this further. 9.8 divided by 2 is actually 4.9 times 2.60 squared. So now let's try doing that. 4.9 times 2.60 squared is actually equal to 33.124. And the unit is meters. However, we have to round off to the correct amount of significant figures. And since the lowest amount of significant figures here is, well, it's actually gravity. However, gravity has a lot of significant figures as well. So the measurement we're going to be using is the acquired measurement, or the measurement that's given in the question, which is 3 in terms of seconds. So we're going to round up to 3 significant figures. That's 33.1 meters. So on the topic of significant figures, please just make sure to ask your teacher or whoever is teaching this subject to you, and clarify which or where your final answer should be based on, aka where should the significant figures be referring to. Should it be the constant, or should it be the given question? Because 9.8 as gravity could actually be 9.81. It actually has a lot more numbers, so it really depends on your teacher. However, in my idea, gravity is a constant in terms of Earth's gravity, so this shouldn't be a value that your final significant figures should be based on. So that should be the answer for this question. Upton Chuck is riding the giant drop at Great America. So that's it, and let's see our final example for UAM. So for this final example in UAM, it's again another free fall example. So that we have 2 examples of free fall and we have 2 examples of just normal kinematics. Okay, so let's do this a bit faster. A feather is dropped on the moon from a height of 1.40 meters. The acceleration of gravity on the moon is 1.67 meters per second squared. So determine the time for the feather to fall onto the surface of the moon. So how do we do this? We need to first again get the given. So let's get the given. Our given is dropped. It says it was dropped. That means its initial velocity again should be 0 meters per second. Now its height is 1.40 meters, meaning if I drop it from a height of 1.40 meters, its change in position should be the same. Therefore, our delta x, or displacement, is 1.40 meters. And now we also have gravity given, which is an acceleration, and apparently the acceleration of gravity on the moon is 1.67 meters per second squared. So now we have to find time. We're required to find is time. So what equation should we use? Let's take a look. So we have initial velocity, we have delta x, and we have acceleration. So let's see which equation here uses these three. We're not given a final velocity, so I think we should use equation 3. So let's check. We can derive time using delta x, we have initial velocity, and we have acceleration. So this is correct. We need to use equation 3. But first step in using this equation is we have to derive. So now to copy paste. Actually, let me just rewrite it. Okay, so delta x is equal to v0 times time plus 1/2 at squared. So if again we want to get t squared, or just t, we need to isolate that first. So we need to go delta x, subtract v0 times t from both sides. So v0 times time is equal to 1/2 at squared. Now we have to derive even further. Let's move this all up. When we derive from here, we have to isolate t squared first. So let's start from there. We'll get this again, except the result of t squared, and delta x minus v0 times time will be divided by 1/2 a, which is also equal to, in simplifying this complex fraction, just multiply a over 2, then flip it around, so it becomes 2 times it becomes 2 times delta x minus v0t over a. So let's rewrite that. And then we have to get the square root of this side. Okay, let's copy this in order to get t squared, the value of t, I mean. So let's remove the squared here. So again, to see how we derive the formula, we first isolate this term here, since t is located on that term, by moving initial velocity times time to the other side, or subtracting them both on each side of the equation. And after that, we have to isolate t squared, so we have to divide the left side by 1/2 a. Now 1/2 a is also the same as a over 2, and when you divide a fraction by a fraction, you just flip the fraction upside down, and the fraction in the denominator upside down, and multiply. So instead of a over 2, it will become 2 over a multiplied by the numerator. And since the numerator is just a set of terms, it's going to be 2 times delta x minus v0t over a. And since the right side is still squared, we have to get the square root. Okay, so now let's remove these excess solutions. And now let's just use this running equation. Plugging in our values, we can actually get this. So we'll have 2 times delta x, which is 1.40, minus initial velocity times time. That's 0. So let's just remove that, because our object was dropped. Now we have to divide this by 1.67, since that's the acceleration of gravity on the moon. And this should equal time. So let's try putting that in the calculator. So we have the square root of 2 times 1.40 divided by 1.67. And now according to our according to the calculator, we should be getting 1.29 seconds as our time. And is that the correct amount of significant figures? Yes. So That's around 1.29 seconds as our final answer. So, yeah, that is all for kinematics and UAM. Thank you everyone for watching this video, and I hope you guys learned something, because this concept is actually one of the most critical concepts for physics, particularly with mechanics, dynamics, and kinematics. So we need to master these topics, as this will also lead us to the next concept, which is projectile motion, which uses UAM particularly on the horizontal axis, because UAM and projectile motion go hand in hand. So thank you everyone again for watching, and I hope I'll see you guys in the next minute concept video. Thank you everyone, and goodbye.